Can see. So the idea again is to make a connection, because this is a gen ed course, repeatedly throughout the term, hopefully between physics and kind of everyday life, your own personal interests or your career interests or ethical concerns of society or more general concerns of society. And physics, although, science in general is certainly acceptable, a lot of times people want to talk about something that we haven't gotten to or we won't get to in this class, like ultrasound imaging or something like that, if they're interested in medicine. And that's totally fine. You just have to make sure that you keep it at a level that someone could just understand without being anyone who knows anything about that. Okay. We're going to sign up. So there's only going to be one per day. And so I'm going to send up an electronic doodle kind of thing. If you ever used Doodle before, where you sign up for one slot on one day, excepting the class meeting before exams and the class meeting of exams, it's pretty much going to be wide open. So choose a day that fits into your schedule. It's going to be in groups of 1 or 2 students. Just the 2 helps us fit them all into the semester more easily. So you get no less credit if you do it in a group of 2 than in a group of 1. And the folks who are on Zoom are just going to present it via Zoom, and we'll just listen through the speakers in the room as if you're doing it here in class. You just have to point in there. Generally, so just a few things to emphasize about making it go smoothly. At the beginning of class, I'm not going to want you to log in as yourself on this computer because it takes me too long to get set up. So what I'm going to do is be on, set up to get to go in class. And then you should be able to access your materials either through a browser, going to your file space through a browser, or bring it on a thumb drive that you can just plug in and access it. Like a PowerPoint presentation, I don't really care too much about the form you use, but PowerPoint is certainly fine, and most people do use that because it's well supported here. Should be between 4 and 5 minutes long. You need to practice it probably a couple of times to make sure it's within the time and that it's going smoothly. So gather a couple of friends to watch and give you suggestions. The main requirements are just the connection with some personal interests, societal interests, ethical connection, any one of those. And science, more specifically physics, is good if you can connect it, but it doesn't have to be specifically physics that we talk about in this course. There's some other details on here, and there is a list of topics, and I encourage you to just ignore the list of topics and think, what do I want to talk about? A lot of athletes will talk about their sport. Divers talk about, that rotational motion in diving. That's good towards the end of the semester. Someone recently did one on pottery because they were taking a pottery art class, and about the spinning motion. We'll talk about rotational motion later on. Sometimes people do kinematics kinds of things, of just shooting baskets or, anything like that. Sometimes people do injuries that are common in their sports. So if you're unsure about whether it's appropriate or how to address it, feel free to ask me. And I also have some guidelines on the back page. Okay, so this is second page, flipping down here to the bottom, because these are 5-minute presentations, and it sounds like, oh, that's easy, I don't have to talk for very long, but it's really hard to actually make something coherent in 5 minutes. You have to have something to suck people in really quickly, get them interested in it, give them a few points, and then repeat something at the end so they can take it away, or leave them with a question to think about if there's some ethical quandary that you're concerned about. There's just not a lot of time, and you shouldn't have many slides either. I'm thinking 3 or 4 or 5 slides or something like that. It's hard to explain something in 5 minutes and have lots of slides. People just get overwhelmed. And part of the point of this is not just for you to get the experience of presenting, but probably the greater benefit is for you to watch a whole lot of other presentations, and that gives you a sense of what works and what doesn't. I know this is a fairly narrow kind of 5-minute presentation, but it can, for me, watching other people's presentations, either I really like what that person did, or I really didn't like it, or it just failed, or I got lost there. How can I avoid that in my presentation is usually the best way to get better. So think about if you want to work with someone else in class, I encourage it. Suggest a topic to each other, and sometime in the next couple of days, you'll get an email with a Doodle sign up thing, and you can put both of your names if there's two of you in the sign up slot. Click on the date that you want, and it will be at the very beginning of that class, the first 5 minutes. So you should be here a little bit early, get your stuff ready, and we'll start right on time, and then I'll go right into where we are in the physics once we get done with that. Any questions on this? I know you haven't read all the details probably, but read through it carefully. If you have questions, I'm happy to answer them on Wednesday or in office hours, whatever. Okay, that was thing one. Thing two is, I guess, to finish up the discussion we were doing at the end of chapter 3, which seems like it's taking a long time to get through, but I just wanted to do one more problem. We did problem 1 at the end of Friday. Problem 2 is only a half a step, more sophisticated than that. Problem 3, I wanted to explicitly illustrate quickly because it's a kind of problem where you might be left wondering, well, where do I even start? It doesn't seem like any straightforward application of the kinematics equations will work. So here's the statement, and then I'm going to go to the board and actually work it out. Soccer ball is kicked from the ground level on a horizontal field. It travels a horizontal distance of 26 meters before striking the ground. That's measured along the horizontal field. And we're told it reaches a maximum height of 10 meters above the ground. Ignore air resistance so that we can use our assumption of constant acceleration in kinematics. And the first question is, for how much time is the ball in the air? So let me unshare this so people can see the screen there. And well, I might think of it, unfortunately, when you're asked about time, there are 4 different equations that the t appears in, so you've got a lot of choices. But, I have 2 numbers. One is how far it goes totally in the x direction, and one is the highest distance it goes up in the y direction. And I might just think, by wishful thinking, let's pick one of them and think if there's a t in it, I can solve for t. What else do I need to know? And then back out of that. So one of the simpler ones might be the y versus t equation. It doesn't have all the squares in it. So for example, Vy equals Vy initial plus Ay times t. Drawing a picture just to go with it, maybe I'm going to have it go up and down like that and choose my axes so that it is at the origin of the xy coordinate system at the point where it's kicked. And we're told that this is 26 meters along here and 10 meters high at the very middle. Now, one of the problems is, if I say Vy final is Vy, what's my initial and final? And your first inclination might be to say, here's initial and here's final, because that's the whole motion. It certainly was in constant acceleration if I do just after the kick and just before it hits the ground. The problem is with those initial and final is I'm not going to ever involve the 10 meters. The 10 meters is in the middle, and so nothing about the initial or the final is going to involve that 10 meters, and it seems like I'm going to need to use the 10 meters. So instead of that, just to involve the 10 meters, I'm going to choose this to be my initial. I'll just write an I there, and this highest point to be the final. I'll write an F there. Okay, so Vy final, let's see what we know in here. Do I know what Vy final is for that initial and final? And for my x and y axes? You don't know what it is for this final state up here at the top? Yeah, it's 0. Why is it 0? Yeah, it's moving horizontally at that moment, right? And we said plus y is up. It's not moving at all in the y direction. In other words, at the very top, at that instant, its velocity is in that direction. What's the y component? Well, I have to say, in going from tail to tip, how far do I have to move along y? Not at all, right? That's what it means for the y component to be 0. It's perpendicular to the y direction. I only have to move along x. And so the y velocity component for my definition of final is 0. Unfortunately, I don't know the initial y component, but if I did, then I'd be able to solve for t, right? Because in my coordinate system, the y component of the acceleration, is everybody in agreement that that should be minus 9.8 in SI units? And therefore, if I could find the initial y velocity component, it's not exactly clear how to do it. It was much easier in those ones where you're given the speed and the angle, then it would be pretty easy to find it. But this is supposed to be a harder problem. How might I find, so I've reduced it down to, if I could find this, then I could find the t that elapses in between initial and final. That's not the total time it's in the air, but does everybody agree that I would just double that time to get the time from ground to ground? And that's just because, you know, if you think of y as a function of t, the picture looks kind of the same, but as a function of time, y as a function of t we know is a perfect parabola if air resistance is negligible. Parabolas are always left-right symmetric. So that means if you're at the vertex, it takes just as much time for it to reach the vertex as it does for it to come back down. And that comes from the kinematics equations, that y is a parabola. Okay, so how might I get at what the initial y velocity is just from those two numbers? It's a little bit disconcerting. What else do I have to work with that would involve the initial y velocity? Here's one of the equations. We already used it. What else involves Vy initial? Well, there's another one that involves the t squared, right? Y equals y. You know, this is okay to just sort of spin your wheels here. So plus Vy 0 certainly appears in there. That's what I'm wanting to solve for. T plus 1/2 ay t squared. That doesn't seem exactly where I want to go because it also involves the unknown t, right? I might be able to reduce it down to 2 equations and 2 unknowns, but let's just hope that we can not use that one because I don't really want to solve 2 equations and 2 unknowns. Let's try the other one. The other one looks like this. I call it the third equation. Vy squared equals Vy initial squared plus 2ay times delta y. Delta y is the displacement in between initial and final. So in this case, you guys already told me Vy final is 0 for my definition of initial and final. Vy initial is what I'm hoping to solve for. So we'll just hold on to that. Ay is minus 9.8. And what's delta y? 10. Between my initial and final. Again, it depends on your definition of initial and final. But for my chosen one, it went up in y by 10 meters. So the displacement in between initial and finals, and I'm just leaving out the units again because we're in SI units here, is this. So this allows me to, here's a negative number, I'll put it over as a positive number on this side, take the square root, and you'll find out that Vy initial is equal to 14 meters per second. That's how fast it was going up at the point it was kicked. And now I can substitute, okay, so we never use this one, let me exit out. And then I can substitute this number up there and solve for t. Okay, this is a little bit of a spaghetti problem here, but it's not too bad. You just have to kind of start somewhere and have some faith that, well, if I only knew this, I would get this. What other equations involve that? And that's one way through it. There are other ways to go through it. We probably could have used this equation too, but I would have gotten 2 equations and 2 unknowns. It would have been a little messier. And we will be solving 2 equations and 2 unknowns. But in any case, that's, what if I entered this, what if this were a quest problem and I entered it in, would I get it right? Because I've already forgotten that the time between initial and final is not what was asked for in part A. How much time is the ball in the air for? That's double that, right? So we need to double t, and that's our answer, 2.86 seconds. Okay, that's a little bit more complicated. Somebody asked in the reading responses something about question B here. What angle above the horizontal is the ball initially kicked? Somebody said it seems a little bit harder if you're not given the initial angle and then you're asked for it later. So let's do B. C is pretty easy once you've done B. So if I imagine drawing in the initial velocity here, let's draw that vector. Initially it's kicked, well, let's just draw it down here. Initially it's kicked, I might just call that V initial, in that direction. And what we want to know is this angle with respect to the horizontal. I'm just going to call it Greek letter theta, as we often call angles. And hey, we just found out that Vy initial, the y component, is 14 in SI units. If I only knew Vx initial, does anybody know how it would be done then, or one step away from being done? From our old friend SOHCAHTOA. Yeah, it's actually tangent from SOHCAHTOA. Tangent is opposite over adjacent. So if I could find this Vx0, tangent of theta is Vy0 over Vx0. And I know Vy0, we just found that in the process of doing part 1 or part A. So if I could find Vx0, then I would just take the inverse tangent. It's going to be a nice angle between 0 and 90 degrees, so I don't have to worry about that adding 180s nonsense.
Dr. Kelly?
Yes.
Can you not just use the displacement for like the X and Y components?
You're going to need to elaborate on that a little bit more.
So like you're using V of X and V of Y to solve for the angle. Why can't you use delta X and delta Y to solve for the angle?
Oh, I see what you mean. Yes. So you're saying, do you mean between my initial and final that I have on here? Or all, because if I go between there and there, there's not much of a triangle I can draw. But if I go between there and there, this is what I was thinking you were saying. Find find that angle there.
Oh.
Anybody see what the problem with that is? Or maybe you're I don't know who's speaking now, but maybe you're realizing it as you're looking at it. The initial velocity vector is along this direction, right? That's the wrong theta. I shouldn't even be calling it theta because it's not the same as this. It's some other theta, theta prime. In other words, the angle I make out of forming this triangle is not the same as the angle that the initial velocity makes with the horizontal. If I took my final to be over here, that would be painfully clear, right? That's clearly not the same angle. So I can't use that. I think that's what you were suggesting.
Yeah. Thanks for clearing it up.
Okay, thanks. So my goal here is just to find the initial X velocity. And notice there's something I haven't used yet. That 26 meters, right? How might I use the 26 meters to get the Vx0? Yeah. Okay, let's write down the third one in terms of X. Vx final squared equals Vx initial squared plus 2ax delta x. And what you're saying is, you want your initial to be here and final to be up there, or final to be all the way at the bottom? Yeah, I would like it all the way at the bottom. We already found the time to go all the way there. You're not using a time equation, but let's see. In this case, what's going to happen here? Delta x, no doubt, is 26 meters. What's kind of a bummer when I plug some other stuff in here? This coefficient in front of that thing is 0. Ax is 0. So that was kind of a bummer. Looks like we're not going to use that equation. Okay, that's fine. Where else might we go with it? I need something with a Vx0, and that kind of goes into all the x equations. Yes. Yeah, I could use the one I crossed out, and I'm just going to, out of laziness, leave the ax term out of there because ax is 0, right? So the one I crossed out would be x final equals x initial plus Vx initial times t. And I got to be clear, I can always change my mind from different parts, what's initial and final. As long as the acceleration is constant all the way, I'm welcome to say, now this is my initial, and now my final is over here. Okay, fine. Then x initial is 0, x final is 26. Vx initial is what I hope to solve for, and what's t? Yeah, it's the total time it's in the air, and that's what we got from our 2 up there. So it's a different t that we're talking about here, 2.86. That allows me to solve for Vx0. The details aren't so interesting, but 9.1 meters per second. And then plug it into here. So this would be, what was my Vy0, 14 over 9.1, and then take the inverse tangent, and you get theta is 56.98 degrees if you're in degree mode. Okay, I just thought I'd do that example because I think this is, if this appeared in the homework, everyone would think this is one of the more challenging questions. I would consider this the higher level kind of things. You see some medium ones in there and certainly some easy ones in the homework too, but just to give you. No, I didn't. I meant to write 9.1. Thank you. I'm so used to writing 9.8 for obvious reasons. No, so I would say then after that, theta is the inverse tangent of Vy initial over Vx initial. In other words, this is just the notation for a function. This doesn't mean flip it upside down. Power to the -1 means flip it upside down, but the tangent with a superscript -1 is just the name of a function. It doesn't mean anything's in the denominator or flipped over. All right, any more questions on that one? I posted these on the website on Friday in case you wanted to look at them, but I thought that one was worth going through just so you couldn't claim that I only did like the very easiest problems in the context of, and then you encountered hard ones on the homework. So keep chipping away. I did change the homework due date to tomorrow night. Someone told me that it was in the morning tomorrow, and then that was just a mistake. So tomorrow night is when it's due. Okay. Now, on to chapter 4, fun stuff. We're making a big transition in the course. Oh, always a problem with this, but let's see if I can get it working. So in chapters 2 and 3, totally not working. Okay, not the end of the world. I can always point over here. I like to be near the screen, but that's okay. In chapters 2 and 3, we were doing what's called kinematics. That just means the process of describing kinds of motion. When someone just tells you, hey, the acceleration is constant. Don't ask why. It's not important. Now we're going to start asking why in chapter 4 and beyond. As opposed to kinematics, this is called dynamics, which means we're going to analyze forces and the ways in which forces determine motion. They're going to determine the acceleration in a way you've read about and we'll see precisely here. Okay, so the first thing to realize is that, we've been using our intuition about forces. People have pretty good intuition about forces. A force is always an interaction between two objects. So for example, if I'm exerting a force on the board, I can feel that the board is pushing back on my hand in this direction, right? If I can feel my weight is pushing down on the floor, but the floor is always pushing back on me. So whenever I exert a force on something, there's another force back on me. It's an interaction between two objects. They each push on each other. Those examples were contact forces, but gravity is another example of a force that's an action at a distance, as we say. Even though gravity is not directly touching this pen as it falls, gravity is exerting a force on the pen. And strangely enough, the pen's also pulling Earth up. It's just that Earth is so massive, it hardly moves at all. The pen does most of the moving when I drop it. Okay. So we're going to describe a lot of forces, types of forces in this chapter. Each force is represented by a vector. That means there's the strength of the force. We'll talk about the units in SI, how hard am I pushing, and then the direction I'm pushing. I can push in this direction on an object or in that direction. There's a magnitude, the strength of the force, and a direction. What's going to be particularly important for us is called the net force. Sometimes it's referred to as the resultant force on the object. And this just means you add up all the forces that are acting on the object. I call it the net force. Sometimes I should also note that in Giancoli, he uses the Greek sigma summation symbol. That I'll write it large since I got my screen shared. It looks like this. So when I write the net force, that means you figure out all the forces that are pushing on an object and you add them up as vectors. We talked about adding vectors, right? The easiest way to usually do is get the components of each of the vectors, and then the x component of this force would be the sum of all the x components of all the forces that are acting. So this is kind of like adding them all together. Giancoli denotes it like this, the sum of the forces. So that Greek capital sigma means add them all up. Those two notations mean exactly the same thing. You'll see me switch between them. When we're analyzing how forces affect motion, we draw things called free body diagrams. And I know you read about this in the readings. This is just a diagram showing all the forces acting on an object and labeled as arrows. So here's some examples that were used in the videos. We'll be doing a lot more in the context of this, for weeks after this. Here's some poor person pushing a really heavy box along the floor, maybe at constant velocity, maybe not, maybe it's accelerating as time goes on, who knows? What are the forces acting on the box? Well, the person obviously is pushing on the box in the picture in this direction, right? Why isn't the box just going faster and faster, maybe? Well, it's because there's sliding friction on the floor. We're going to have to describe something about friction, but everybody has the intuitive notion that I've got to I'm pushing in this direction, friction's kind of pulling back in the other direction or pushing back on the box. So friction would be a force in that direction. Gravity's pulling down, that's the weight of the box. So gravity's pulling it towards the earth. That's why it's so hard to lift up. Why isn't it accelerating downward or falling towards the earth? Because the floor is pushing up. So I can identify at least 4 forces here. And when we draw a free body diagram, we usually do something like this. You have to first of all specify what object your free body diagram is for. So here it's the box that's being pushed. And we just draw all the forces on it. And in this case, the force from the floor, sometimes people call that a normal force, and we'll talk about that later on. Here's the applied force from the person. It's being pushed to the right. Friction is opposing that force, so it's going back opposite the direction that he's sliding it. And gravity is trying, the earth is trying to pull the box down, but the floor is pushing up, so it didn't succeed in making it move. Okay, then again, I'm appealing to your intuition about forces. We're gonna look at these in detail as we go on. Here's an even simpler one. Coffee cup sitting on a horizontal table. Gravity's pulling it down, but it's not falling because the table is pushing up on it. So there are 2 forces that we can identify there. Notice that I'm not doing any great artistry in the free body diagram for how I draw the object of the free body diagram. You got to know what it is, but I don't need to draw a detailed picture of a mug. That's just a waste of time most of the time. Okay, so the connection between forces and motion is Newton's laws. So we're going to go through these one at a time. And first, Newton's law, which is kind of the most confusing of the 3 laws. An event can always be viewed from the perspective of many different observers. If I have an object here, let's take a ball. Let's suppose I'm an astronaut in outer space, right? And pay no attention to the board. I'm floating here in space, right? And I'm looking at the ball and it's floating in front of me. That's one way to observe it. And I would say, from my perspective, the ball's just sitting at rest. right? I'm floating in space and I see the ball in front of me sitting at rest. Well, that's just one person's perspective. Here I'm imagining they're in some sort of space pod or something and just sitting there watching it. Another person, observer B, might be looking at the same ball, but they might be looking at it as they cruise by at a constant velocity. So if I'm that person, right, if I'm in the space pod and I'm watching this ball, I'm looking out the window, I actually feel like I'm at rest. And I saw a ball zooming in that direction. The ball would say I'm moving in this direction. But from my perspective, I just feel like I'm sitting there and the ball seems like it's moving in that direction. So is it moving or not? Depends on your perspective. Here's an even more confusing case. Someone could be looking at this ball, which to me is perfectly at rest, or maybe it's moving at constant velocity, and they start accelerating. So you may say, hey, that ball is not accelerating, but someone else would say they looked out the window, hey, it's going faster and faster in that direction as time goes on. So it's accelerating too. So whether something's accelerating depends on your point of view. Very quickly, this can sort of get out of control where you don't really know what ground you're standing on. So Newton's first law is going to help us restrict things, the ways we're going to look at things, the perspectives we're going to take when we look at objects or events. Newton's first law, this is my own, probably Gene Colley has a slightly different wording of it. One can always find a perspective from which to view an event or an object where every object with zero net force on it moves with constant velocity. So for example, no, I guess I should click forward. Such a viewpoint is called an inertial reference frame. And we're always going to use inertial reference frames to analyze motion. In fact, Newton's going to tell us what to do if we're observing from an inertial reference frame. So as an example, here's a ball, we're in deep space. No big stars or planets nearby. Nothing is pulling on this ball, right? And here I am floating in space. I'm looking at the ball and I say, I'm looking around for sources of forces, things that might be pulling or pushing on it, and I don't see anything nearby that should be pulling or pushing on it. So there's no net force on that ball because there are no forces pushing on it. The net force is zero. And therefore, if Newton's first law is true, if I can I find a perspective in which it's moving at constant velocity? Well, no net force on it, and I see it moving with constant velocity. That constant velocity is zero velocity sitting at rest. That's one way to have a constant velocity. So I would conclude, hey, that's a little bit of evidence that I'm observing this from an inertial reference frame. My perspective of observing is one of an inertial reference frame there. As opposed to if I saw an object and I said there's no forces on it and I saw it start accelerating in one direction, I would say I'm probably not observing from an inertial reference frame. And we'll see examples of that in a bit. Okay, so taking that definition for granted, here's a little voting question. As seen from an inertial reference frame. So the claim is the view we're seeing from here is one of an inertial reference frame in which objects with no forces on them travel with constant velocity. No net forces on them travel with constant velocity. Here's a car rounding a curve. We're looking at it from above while maintaining constant speed. So maybe it's going at 5 miles an hour the whole way while it turns around in this semicircle. Is there a net force on the car as it rounds the curve if this is being seen from an inertial reference frame? Let's just see a quick vote. I know I didn't give you enough time, but I want to see if somebody can help verbalize it for me. The ones I'm seeing held up are by and large almost all B's. Yes. Who wants to explain why we can conclude that there must be a net force on the car during the process of that motion when it's going around the curve, given that the perspective we're seeing it from is one of an inertial reference frame? Yeah. Yes. So its velocity certainly is changing as it goes around because velocity is a vector. And if the vector changes at all, it could change by changing its length. That would be speeding up. But this one happens to be changing by changing direction. Velocity vector is changing, and therefore the velocity is not constant. And from an inertial reference frame, if I'm observing from an inertial reference frame, if velocity is not constant, the only way for that to happen is if there's some net force. That means there's some forces being applied to it that don't all add to zero. They have to add up to some non-zero net force. If there were no, another way to think of it is backwards. I'm observing from an IRF, so if there were no net force, it would be going in a straight line at constant speed, right? That's what constant velocity. It's not doing that, and therefore, if I'm observing from an IRF, there must be some net force on it. Okay, so the answer there is yes. Now, what's going to really concern us, and especially in Newton's second law, is when viewed from an IRF. So we're not going to take these crazy perspectives where things appear to accelerate because we're observing them from a point of view that accelerates. We're not going to allow that. Newton's going to just sort of not speak about that, really. When viewed from an inertial reference frame, how do forces affect the motion of an object? That's the subject of Newton's second law, but in between there, we better talk about mass, because the relationship involves the mass of the object. Many of you have heard of F equals ma, that's where we're heading, but we need to know what the m means in F equals ma. So mass is sort of, one way to think of it is in terms of inertia. Inertia and mass mean the same thing. They're just different words for the same thing. It's a measure of the resistance to change of state of motion of the object. So if an object is floating out here in space, right, and I give it a push and it starts accelerating really quickly, that means it was really easy to change the state of motion of the object. What I conclude is that the mass is very small. It's easy to change the state of motion of the object. If it's going by and I flick it with my finger and it changes the state of motion, then I say, oh, it must be something really light. If it were a lead ball, I would, beyond hurting my finger, it would probably just keep going in the same direction. So it would be harder to change the state of motion of the object. Okay, so mass is a measure of that. Now, confusingly, for people who are new to physics, mass often gets confused with weight, but weight is different. So mass is something that is intrinsic to an object. If I've got a massive object, so here's a pretty hefty piece of brass. Here on Earth, there's a great gravitational pull on it towards Earth. And that pull, it's a force. Gravity is exerting a force, which is great. And I can feel, because to hold it steady, I have to push up hard with my hands. That is called the weight of it, the strength of the gravitational pull. This object has a certain mass. Now notice, if I brought it out to deep space and I put it on my palm, I wouldn't even have to put it there, it would float above it, right? I would say, this object has zero weight when I'm out in deep space, but it has the same mass. It's still just as hard to get it going on the surface of Earth as it is in outer space. Its mass is intrinsic to it, whereas its weight depends on, is it near a big body with a large mass that's going to be pulling on it through gravity. So mass is just how hard it is to change the state of motion of an object. Weight is what we use. Now, the two clearly are proportional here on the Earth's surface, because when we use a scale and we measure the mass of this by putting it on a scale, it's not measuring the mass, it's actually measuring the weight. But the scale knows the constant of proportionality between them, and it just converts it into a mass units, right? Because it knows how hard the Earth would be pulling on a mass. That scale wouldn't work correctly, it wouldn't be calibrated correctly on the moon or in deep space where things aren't being pulled on as hard or at all. So if you, just to push the point a little bit, if you were an astronaut in outer space and you saw this floating in front of you and you said, I don't know if this thing is solid or if it's actually just a thin shell and hardly has any mass at all. But I can't put it on my hand and feel any heft because I'm not near any big gravitational forces that are going to be exerting a weight force on it. So it's floating there in outer space. How would you judge whether it has a large mass or not? Same way I just said, right? I could flick it, try to push it, take it and shake it. You know, when things are heavy, they're hard to accelerate back and forth, whereas they're light, you can really shake them fast like that. So what I'm doing is seeing, when I shake something, I'm seeing how hard it is to change the state of motion of that object. Our SI units for mass are called kilograms. Maybe many of you don't have an intuition about how heavy a kilogram is. This is a kilogram. I'll pass it around. Maybe we shouldn't because it's the COVID days, but kilograms, it's a little bit more hefty than a couple cans of Coke or something like that. So it's not, that's metal, so it's a lot more dense than water is. So if you think of 2-point-something cans of Coke, that's about what a kilogram mass is. So we're going to be using kilograms all the time. All right, now that we know what mass is, we can talk about Newton's second law precisely. Newton's second law says when an object is viewed from an inertial reference frame, in other words, when there's some motion or interaction between objects, or we're just looking at one object, and we view it from an inertial reference frame so that if there are no forces on an object, they move with constant velocity. Then the net force, or the sum of all the forces, is how Giancoli would probably write it. The net force on the object, that means add them all up as vectors, is equal to the mass of the object times its resulting acceleration, or the acceleration it's undergoing, is true at that moment and in every moment in time, no matter what. I just want to make sure that you understand there's no exceptions to that. It happens all the time. Doesn't matter whether the object is accelerating or it's just sitting there at rest, it's always happening. The net force equals the mass times the acceleration. Okay, looking at the units here, because we haven't talked about the SI units for force yet. We just introduced that masses have an SI unit of kilograms, and you already know that the acceleration has an SI unit of meters per second squared. So forces must have an SI unit, by our discussion in chapter 1, of kilograms times meters per second squared, kilogram meters per second squared. That gets used so often that there's a shorthand. So newtons, which is denoted by N, is just shorthand for kilogram meters per second squared. So we'll be measuring forces most often in newtons, although the English unit is pounds. So people are familiar with pounds of force, perhaps. That's telling you how heavy something is. That's the gravitational force. Okay. I mean, if you watch the videos on this over the weekend, then this gave it away, but let's just try this voting question here. There's always some amount of discussion, at least when people haven't heard this before. You're a passenger in a car not wearing your seatbelt. So we've all experienced this before. Imagine, except you probably always wear your seatbelt now, hopefully. Without increasing or decreasing speed, the car makes a sharp left turn and you find yourself colliding with the right-hand door, right? If someone yanks the car to the left, right, just suddenly turns left. If you're the passenger in the passenger seat, you find yourself thrown to the door over there. What's the correct Newton's second law analysis? Analysis in terms of inertial reference frames, how to think about the relationships between forces. A, while you're moving toward the door and after you collide with the door, there's a rightward force pushing you into the door. That's why you collided with it. B, starting at the time of your collision with the door exerts a leftward force on you. C, both of the above, or D, the dreaded neither of the above. Okay, at least 2/3 of you in the class are showing signs of being ready to vote. So hold up your vote so I can see it, and let's see if there's a consensus here. It's really in the room between the B's and the C's mostly. There's not a clear winner. Rather, and sometimes I'll have you talk back and forth with your neighbors, but maybe I'll just have a discussion here together. Who wants to state why they voted for B or C? How about a B first, because you don't have to explain two things. Yeah, Newcomb.
You start thinking, you're like the force vector sort of angular, right? So you're pushing it through the door pushing back.
Yeah, I mean, it's like the discussion I had about forces. There's always, when one thing pushes on another always pushes back on the one, right? I mean, they always push on each other. So if I feel myself pushed into the door is clearly pushing on me, or at least if you believe that discussion. I think most people have that intuition. So that's an argument in favor of B being true. You want to continue on and say, why not A?
So after you make the turn, I guess it depends on how long you're like that implies that you're off the course. So like you're going right, or I guess you're going left, but there's no more force like you centralize, you neutralize that response to the door.
So which one are you disagreeing with? The first part, while you're moving towards the door, there's a rightward force pushing you to the door, or after you collide with the door, there's a rightward force?
I agree with both parts.
Disagree with there being a rightward force pushing you into the door afterwards, okay? Anybody else have a comment on that? Or clarification?
I think that A is the correct second part as well, because I was thinking about like what happened, like you like trying to hard like get yourself back straight out.
Yeah. While you're turning, it certainly is hard to pull yourself away from the door, right? And that seems to suggest that there's some sort of force pushing you into the door. It's almost like you're magnetically attracted to the door. Now, I know we haven't talked about really any forces yet, except weight a tiny bit. What do you think the source of, if you believe that when I'm going along and all of a sudden I find myself flying towards the door and then I'm smashed into the door, it seems like there's something pulling me towards the door and then keeping me smashed against the door while we're turning at least. What would be the source of that? In other words, what is the object that's pulling me towards the door? Is the door suddenly like turn on a force that pulls me over towards it? Yeah. Well, momentum is not a force. Momentum is a way of describing just how when you go in a certain direction, you tend to keep going in that direction. But yeah, I mean, you might, it's so a related concept might be inertia, right? You tend to want to keep going in the same direction. The correct answer here is actually just B, and A is not correct. I wasn't sure I totally followed how Newcomb was saying it there. But if you look at the following picture, the problem is from your point of view, as you start rounding the curve, you're not looking at things from an inertial reference frame. One way to think about that is as I'm going around a curve. So I'm looking at something that has no net force on it, right? Here it is. If you're confused about it, just think of it as floating in outer space, right? And I am riding in my spaceship. I see no forces on it, and yet I see it wildly turning as I look out the window. Oh, there's something like turning around in a curve as I'm curving around. No net forces, and yet it's not moving with constant velocity. So that means when I'm turning around at a curve, I'm very likely observing things from a non-inertial reference frame. If I want to observe this situation from an inertial reference frame, I better take the perspective of someone who's not riding along in the car in order to be able to think about it like Newton. So what I'm going to do is just imagine looking down from the sky and watching the car going straight and then suddenly taking a curve. Okay. Here we are looking down from the sky. You're in the passenger seat. And as a couple of people over there said, you tend to want to keep going straight. The car was turned in this direction. You can think of the wheels were turned and the road started forcing it to turn in that direction through friction on the tires. Was there ever anything as the car moved like this and you ran into the door, was there any force that was pulling you into the door from this perspective? This is an inertial reference frame perspective here. There isn't. No, I was trying to go on my merry way, going straight, and the car came around and smacked me in the arm, right? I was trying to go straight, and the car came around and hit me in the arm. That's the perspective of an inertial reference frame. We'll find out that it's very difficult to come up with some kind of force that would all of a sudden pull you into a door. What is that force? It's not like there's a great mass over there exerting a gravitational force. It's not like there were electric forces that suddenly got turned on or other kinds of contact forces, because I wasn't even in contact with the door. So Newton would say there was no force pulling you towards the door. That was just a mistake of thinking that it seems like there's a force because you accelerated towards the door. But accelerations can just appear sort of out of nowhere when you're observing from a non-inertial reference frame. When I'm riding around in a car, I'm looking at things from a non-inertial reference frame. You generally want to sort of stay where you feel like you're not accelerating at all to observe from an inertial reference frame.
Is that the kind of the same idea, like when you take it up, swing it around in a circle and the water doesn't come out? You push it to the side, really push it to the
Yeah, it is. And we'll talk about that in detail later on. But yes, I mean, most people, when they're thinking about that problem, don't take the perspective of the water. But, you know, it still seems somewhat odd that the water can go over the top and not fall out. So we'll talk about that later on. But yeah, sort of similar kind of thing. The water is being smashed into the bucket the same way you're being smashed into the door, just by virtue of this thing turning in a circle. Okay, okay, that seems confusing to you. Don't worry too much. Most of the time, you will tend to view things, you will want to view things from an inertial reference frame, and your intuition will be right. It's just that if ever things seem strange and some force seems to turn on and it comes out of nowhere, the warning here is just ask yourself, might I be observing from a non-inertial reference frame? In this case, viewing myself as the passenger of the car, that's what I'd be doing. Here's another case, and I won't linger on this too much, but you're in the space shuttle. You drop a hammer in front of you, except it doesn't drop, right? You've seen videos of the space shuttle, it's just floating there, right? And so there, it doesn't accelerate in any direction. And yet, someone watching from Earth is seeing the hammer go around in a circle around the Earth. How long does it take that? How long does it take to go around the Earth in the space shuttle? Something like, it's not that long, right? It's less than an hour, is that right? Nobody knows. But in any case, you watch it, you're going to see this hammer go around Earth in a circle. Now, if there were no force on the hammer, it should be going in a straight line. That's what Newton's telling me. And yet it's going in a circle. So there's got to be a force on it. And yet when I'm sitting there as an astronaut watching the hammer in front of me, it's just sitting stationary. So it's not accelerating. So according to Newton, who's got the better analysis from the point of view of Newton's second law? Who's looking at it from an inertial reference frame? The people on Earth. That's right. So this thing definitely has a net force on it. The Earth is pulling on it, even though you're somewhat far away from the surface of the Earth. When you're in the space shuttle, you're still close enough that that's what's keeping it in a circle, right? Just like the whole space shuttle is orbiting Earth, that hammer is orbiting Earth too. And so there's a net force on it, and there must be an associated acceleration. If I, the astronaut, say, hey, there's a big Earth down there, and yet I let something go and it just sits still, that doesn't seem to make sense. If that's the only force on it, it should be accelerating. And if I don't see it accelerate, I'm looking at it from a non-inertial reference frame. Okay, now again, we're not going to see these kind of weird cases very often. It's just a reminder that in the back of your mind, if something seems off, you might think if you're happen to be looking at something from a non-inertial reference frame. Okay, so the rest of the chapter, all we're going to do is study lots of different kinds of forces and practice applying Newton's laws. Okay, so the first force that we're going to discuss here is the one we just talked about, the weight force, the gravitational force on an object. Associated with every mass when it's near the surface of Earth or any other planet or the moon or sun, there's a gravitational force, and that gravitational force is called the weight. Here's the formula for how to calculate the weight of an object. The weight is a force, so I've drawn it as a vector here, right? The direction of that gravitational force is downward towards the center of Earth if we're talking about on the surface of Earth what the weight force is. So the weight force is down. To calculate it, you multiply the mass of the object times little g. Little g is that 9.8 meters per second squared number that we encountered earlier. And the direction, notice I've written little g as a vector here. The direction of little g is the direction that things would accelerate in free fall. So the direction of little g here is downward. And, you know, if you drew a planet, here's Earth. Of course, there's all different sides of the planet. So little g here is going in that direction. Little g in there is going in that direction, right? It always points toward the center of the Earth, no matter where you are. Okay, so you can see weight and mass are proportional to each other, and that's why scales can measure weight and infer mass. They just, you know, divide out little g, and then output the number in kilograms, if you like, if you wanted to calculate the mass. That little g, we talked about it being 9.8. Now that 9.8 is only right near the surface of Earth here. Near other planets or in other places, it has different values. In deep space, it might be very close to 0. On the moon, it's about 1/6 of the value it has on Earth. So things aren't as heavy. Even though they have the same mass, their weight is less. It's about 1/6 on the surface of the moon. Okay, so there was a mystery that we're now in a position to explain, and that was what Galileo observed. I hate to drop something so heavy on the floor. I don't want to damage the floor, but Galileo observed that as long as something doesn't have too much air resistance like a feather, things tend to accelerate at the same rate, right? So they'll hit the floor at the same time, even though one is being pulled really hard by the Earth. Why doesn't it get down faster? This foam ball is not being pulled nearly as hard. Here's a justification for that. For Galileo, that's sort of a mystery. Something's pulled so hard, I can feel the weight in my hand, and yet it accelerates at the same rate going down. The argument is, well, let's do F net equals ma. We know how to calculate the weight force. So if I drop something and it's in free fall, the net force, which is the sum of all forces on it, and we said when something's in free fall, so I'm imagining an object just falling down towards Earth, the only force on it is the weight force. The weight force we said we can calculate just by taking the mass of the object times little g. Okay, that's just the F net part. Now let's set it equal to ma. Set the net force equal to ma and focus on that last equality there. If I focus on the last equality, there's an m in each case, and I can just divide both sides by m. And that means that the acceleration is going to be equal to little g, regardless of the mass of the object, because the mass canceled out. One way to think about it is, yes, the force is bigger on this from Earth, but it also has more inertia. That's what mass is. So it has a bigger force, but it's harder to accelerate, and those two effects cancel each other out, resulting in exactly the same free fall acceleration here. I know it still doesn't seem like that deep of an explanation, but at least it's one level deeper than what we did before. Okay, let's, 2 minutes left. We've got time to talk about Newton's third law without any practice with it. As I said, when I pull on an object, the object pulls back on me. A lot of times I pull on a door handle, but here, here's this thing. I'm pulling on this table in this direction, and I can feel it trying to pull me in that direction. That's sort of a very loose association. Newton's third law tells us exactly how those two forces, the force of me on the table and the force of the table on me, how they're related. And they're related in that they're exactly opposite direction vectors from each other. When I push on an object, the object pushes on me. So I'm pushing this mass up, it's pushing on me downward. I'm not concerned with the gravitational forces. It's a contact force between me, my hand, and this object. It's pushing down on my hand, I'm pushing up on it. Those two forces are equal and opposite as vectors. So the force of A on B is the negative of the force of B on A. And remember, when you take the negative of a force, when you scalar multiply it by -1, it just switches the direction. So those two forces are in opposite directions. And they're sometimes called a third law pair. The pair of objects, when you concern the forces that one is exerting on the other and the other is exerting on one, those two objects are called a third law pair, or sometimes the forces are called a third law pair. Okay. If a car is parked at rest, it is true that the downward gravitational pull of Earth on the car and the upward contact force of Earth on the car are equal and opposite. Why is it true? So here I am standing here. My force, the gravitational pull of the Earth down on me through gravity is exactly equal to the upward force from the floor on the bottoms of my feet. You can take that as true. Why is it true? The two forces form a third law interaction pair. The net force on me is 0, or neither of the above. Very quickly, because it's exactly time to leave. All right, I'm just going to make a very okay, it looks like mostly A's. The two forces form a third law interaction pair. It seems like they would, but they're actually not a third law interaction pair. Remember, when there's a third law interaction pair, we're talking about the force of one on the other and the force of the other on the one. Here, the two forces are the gravitational force down on me and the upward force on me from the floor, right? Or in this case of the car. Earth's pulling down on the car and Earth is pushing up on the car. Notice the thing that the force is being exerted on is the same in both cases. We're talking about forces on the car. They can't be a third law interaction pair of those two forces because the forces are on different objects. It's the force of A on B and the force of B on A. They're never on the same object. That's just a little bit of terminology there. All right, we'll continue with this, and next time, Wednesday, we're going to do a bunch of problem solving. Tomorrow, for those of you who have lab, we will be doing some practice with two-dimensional kinematics, a little experiment, and some problem solving practice too. So that'll help us sort of solidify that understanding from chapter 3. See you soon.